In this video, we'll introduce the basic features of a distribution of sample statistics. In the previous videos, we looked at an example where we were flipping a coin 60 times and asking what proportion of times we flipped heads. And we created a distribution of sample statistics showing each time we flipped 60 times what proportion of heads we got. One time that we flipped the coin 60 times, and 35% of those flips were heads. And many times we flipped the coin 60 times, and 50% of those flips were heads. So these dots represent a sample statistic. So this dot, for example, here is a p-hat. And this dot here is a p-hat. It's an example of flipping the coin 60 times and the result we got in our sample. It is a resulting p-hat for that sample. So really, this is a more theoretical distribution to show what we got. You'll see that each of the little dots represents a p-hat. So each dot in our simulated distribution of sample statistics is a p-hat. P-hat, sample statistic. P-hat, proportion of success in the observed sample. Similarly, if we consider the other type of distribution of sample statistics, which is the quantitative data, remember, we are sometimes interested in understanding the population mean mu. And so we go out and we gather a sample and we calculate a sample statistic x-bar. In the previous video, we looked at the example where we went on campus and collected a sample of students and collected how many hours per week they worked last week. And then for our entire sample of students, we calculated the sample mean x-bar for that group. We did this over and over. So we said, for example, one sample mean was about 26.8, I think this was. Another, we had one time when we got like 23.4. There were many samples where we went out and the sample mean turned out to be about 25 hours per week. Each bar in this distribution represents the number of times that we collected a sample and the sample mean was that high. So lots of times it was 25 hours per week. Only once it was about 23.4 hours per week on average. Like 3 times it was 26.8 hours on average. So again, notice that these little squares represent sample statistics. They represent sample means x-bar. So a more general theoretical way to draw that distribution would be like this, that each of those dots are little x-bars. Each of those little squares are little x-bars. So each of these squares is an x-bar. A different sample collected and calculating a different x-bar. And they're counting how many times we got each one of those x-bars. So again, each little square in our distribution of sample statistics represents a sample mean x-bar. X-bar is a sample statistic. It's a distribution of x-bars, a distribution of sample means. Next, let's consider in general then what these distributions' features are. So first, you'll notice the shape of the distribution of sample statistics. As you increase the number of repetitions, that times that you actually go out and collect a sample and jot down the p-hat, and then collect another sample and plot the p-hat, and collect another sample and plot the p-hat. The more you do this, the more your distribution of sample statistics will begin to resemble a symmetric bell shape. It'll have this shape to it. This is true for your distributions of p-hats, and it's true for your distributions of x-bars. It's true for all distributions of sample statistics. They will have this bell shape to them. They will be symmetric, meaning if you draw a line right down the middle, you'll have about equal quantity of p-hats on the left side and on the right side. If you do it for the x-bars, same thing. you'll have about equal number of sample means that are higher than that middle value and an equal number lower than that. There are more values that occur near that center value. Now think about that logically. That makes a lot of sense. For example, in the flipping coins example, we had 50% right in the middle. We were flipping a fair coin. If you were flipping a fair coin, it would make a lot of sense that when you flip the coin and do a sample, there'd be a lot of sample statistics, p-hats, that would come out near 50% heads. And there'd be very few p-hats that would be a lot higher than 50% and a few that would be a lot lower than 50%. Similarly, if you went out and you knew that the population mean is 25 hours per week worked on a certain campus. So say it's 25 hours per week. That'll actually be right in the middle. And then it would make sense that if you collected a sample, you'd get a lot of sample means that were near 25 hours per week. It would be rare that you would go out and collect a sample that was much, much higher than 25 hours per week worked on average. And it would be rare that you would find a sample mean that was a lot lower than that 25 hours per week. So this bell-shaped symmetric curve is what you can expect to see for your distribution of sample statistics. Then the other thing you need to understand is that the mean of the distribution of this sample statistic is what we refer to as the middle, the value at the center of the distribution. It's this vertical line value here. So for our flipping coin, it was 0.5, right in the middle of that distribution. We call that the mean of the distribution. And for the hours worked, the mean was 25 hours per week. It's that value right in the center. And it turns out that that value right in the center is the population parameter. So for the flipping coins, we would be saying that pi, the population proportion, is actually right in the center of that distribution. It's 0.5. It's 50%. If you flip the coin forever and ever, in the long run, it would flip the heads 50% of the time because it's a fair coin. And this one was 25 hours per week is the population mean, meaning if you talk to every single student on campus, and you averaged up all their hours, you would find that the population mean was 25 hours per week. Lastly, standard error. Standard error is the standard deviation of a distribution of sample statistics. It is the average distance that the sample statistics are from the mean of a distribution. Now, in a computer simulator that we're going to be working with for most of the semester, it will actually give you this value, but I want you to understand that if you have a distribution of sample statistics that's really spread out like this versus a distribution of sample statistics that's kind of skinny, like this one, the one that's more spread out would have a higher standard error or higher standard deviation of the sample statistics because the data values would be more spread out. So on average, they're farther away from the center of, and that's what standard error, standard deviation is measuring, average distance from the mean of the distribution. So if they're kind of more squished together towards the mean like this will have a lower standard error because they're not as far away. The distance, the average distance of each dot is lower than this other spread out distribution.